everyone, my name is Kevin. I am a staff engineer at Shopify, and I am here today to talk to you about Ruby's and encodings. So I work in a group at Shopify called the Ruby on Rails infrastructure team. We're basically tasked with ensuring the longevity of Ruby. One of the nifty things that we think about at Shopify is how can we ensure the company will be here 100 years from now? And since we're so heavily invested in Ruby, that largely means how do we ensure Ruby will be a relevant technology 100 years from now? So we do all sorts of things. We have people working directly on Ruby and Rails, fixing bugs, improving performance, adding new features. We focus on the developer experience. If you caught Jenny's talk earlier about supply chain security, that's another thing the group does. I work on Truffle Ruby, which is an alternative implementation of the Ruby programming language. We have an emphasis on very high performance. By being a new implementation, we're not bound by some of the design decisions in C Ruby. So we're able to optimize things in ways that C Ruby is unable to do so. We try to maintain a very high degree of compatibility, though. We can run native extensions, and we're working on production deployments right now. So yeah, the three-encoding problem. The reason I want to give this talk is encodings are one of these things that I find a lot of Rubyists don't have a good handle on. And you can get very far in Ruby without really understanding encodings. Up until Ruby 1.9, encodings really didn't even exist in Ruby the way they do today. But you can get very far with it because it's a very powerful abstraction. If you don't understand encodings, when you invariably run into an issue, you're bound to resolve it incorrectly, which can lead to loss or corrupt data. So to get started, we'll just take a peek at Ruby strings. This is about as simple as it gets. We have a string literal here, and I'm using the magic comment syntax to associate the encoding with the string as US ASCII. Ruby gives you a lot of API calls to kind of inspect strings and dig into their internals. So here we can see that a string is made up of bytes. And the string had 3 characters, the ABC, and this will be the bytes for them. And then we can also get the associated encoding with the string. So a string in Ruby really is just an array of bytes and an encoding to make sense of those. And what we get out of that is an array of characters. At the simplest level, an encoding is really just a mapping function. It takes an array of bytes in and produces an array of characters. There's different encodings, so you can have different lists of characters, and then you can have different byte representations for them. So pausing for a moment, I just want to clarify some terminology. Throughout the talk, I'm going to be using kind of loose terms. If you really get into encoding, there's some very, very precise definitions on things. But for our purposes, we'll consider encoding to just be this mapping of a byte representation to a character. Character, that really is a difficult one. We have printable and non-printable characters. Anything that you can put in a string, we'll just call a character. So it includes all the major writing systems, punctuation, digits, and so on. Then we have code points. And if an encoding is a map of bytes to characters, then it stands to reason that an encoding has a set of valid characters. And all a code point is an index to one of those characters. And then there's also code units, which we won't talk about too much, but code unit is just a fancy way of saying how a code point maps to bytes. So Ruby just kind of uses bytes, but if you look at some of the Unicode stuff, they'll use the term code point, and you can just mentally substitute bytes for that. So revising our definition a little bit, we have 2 levels to an encoding. We have encoding that takes a code point that index into the list and gives you a character, and then we have a mapping from bytes to a particular code point. So Ruby allows us to also check the code points for a string, and you can see everything lines up here. So given that string ABC, we get the set of bytes, list of bytes, because order matters, and there's 3 of those. Then those map directly to the 3 code points, and in this case, they have the same values. That's why I used ASCII. That was by design. That's not a requirement, and I'll show some examples in a bit where that doesn't map up. And then for each code point, we have a corresponding character. So unfortunately, to really understand encodings, we do need to take a look at some of the history here. I know it's not the most exciting topic, but just bear with me. If you haven't heard of it before, there's ASCII, which is the American Standard Code for Information Interchange. This was a very popular encoding, particularly in American businesses and computer science. And with ASCII, we have 128 characters. Of those, only 95 of them are printable. So this is a really restricted set of representations. And everything fits into 7 bits, because when ASCII was created, being able to represent in 7 bits was a benefit over 8 bits. So this loosely corresponds to modern English. We can handle the letters A through Z, lowercase, same thing, uppercase, digits, some punctuation, and a selection of symbols. And then there's other things like control characters, which tell the computer to go do something, like inserting a new line. And we have white space. And then ASCII has its own history that it kind of supports. So there's some characters for ringing a bell for old-style terminals. What you can see is it's really quite restricted. And I think this has even influenced how we write certain things in English. For instance, we have prices that might be more naturally represented in cents, but there is no cent symbol, so we write them as dollars instead. And we can represent like the word resume, but not the word resume. And I think over time, at least in the US, we've just dropped putting those accented characters in. So ASCII was around for a really long time. So any language that really wants to see widespread usage needs to support ASCII. And Ruby does this at 2 different levels. So you can look at an encoding and ask if it's ASCII compatible. And in this case, we're using US ASCII, which will trivially be ASCII compatible. And we'll dig into that in a little bit. And then on a per string basis, you can ask if it's made up of only ASCII characters. So that is, all the characters in the string, are they drawn from that ASCII encoding? Of course, the world is much bigger than the US, and we can't even represent everything that we would in English. So we've collectively needed to move beyond ASCII. And there's been a lot of different ways this has been proposed. There's a ton of different encodings out there. But I'm going to focus on UTF-8. So taking this string tray, the French word for very, it logically has 4 characters, but it takes up 5 bytes. So I tried to line things up in the array here, but that 3rd character with the code point 232, you can see that value is greater than 128, which was the max range of ASCII, and that maps to 2 bytes. Which brings us to Unicode. If you're not familiar with it, Unicode is like probably the most popular encoding system in use today. There's a big standards body for it. Unicode creates these version releases. It currently supports 150,000 different characters, includes writing systems for all sorts of world languages. It has even new control characters that allow you to flip the reading direction of text and things like that, additional white space characters. But one thing about Unicode is it has to try to resolve differences, because writing systems and languages are cultural, and throughout time, different cultures have used roughly the same alphabet or the same encoding system. And like in the modern era, they might disagree on how certain things should be interpreted. So the Unicode standards body tries to resolve these, but it often doesn't do it satisfactorily for all. So while Unicode is in widespread use, it's definitely not the only encoding out there. Complicating things a little bit is Unicode defines these things called transformation formats. So Unicode has this 150,000 characters, so there's 150,000 code points. And Unicode tries to be ASCII compatible in the sense that each of the ASCII code points map to the same in Unicode. But we still have to represent those as bytes in one way or another. So UTF-8 is probably the one you're most familiar with, and this is what's known as a variable width encoding. So each character in UTF-8 can take up between 1 and 4 bytes. UTF-32 goes the other way. It's really simple. Everything takes up 4 bytes. That's 2 to the 32. It represents everything in Unicode, but the downside is every character takes up 4 bytes, so it's not terribly memory efficient. And UTF-16 sits somewhere in between, where, because it's 16 bits, it can represent 65,000 characters or so inside of one of these code units. But if you need to move beyond that, then you need 2 of them. You probably won't use UTF-16 and UTF-32 that frequently in Ruby, but UTF-16 comes up with JavaScript, so if you're doing web development, that might be something you run into. So that's kind of encodings in a nutshell. Ruby, on top of that, has a very rich system for interfacing with encodings. So Ruby is pretty unique, I think, at least in terms of the modern VM-based kind of scripting languages. Most languages nowadays will have a unified internal representation of strings. So if you're working with C, like that predates all of this, but JavaScript, for instance, represents all strings internally as UTF-16. So it can interface with other encodings, but it normalizes everything and does this kind of conversion process. Ruby doesn't do that. For one reason, Ruby tries to be a bit more inclusive than you might see with some other languages, and it acknowledges that the entire world isn't using UTF-8 or Unicode. So as a consequence, Ruby can actually work with these other encodings quite efficiently. It doesn't have to do any kind of conversion, but the flip side is Ruby has to now handle multiple encodings pretty pervasively. So there's this encoding class in Ruby. You can call .list on it and get the list of all the encodings. It ships with over 100 out of the box. And getting back to that ASCII compatibility I talked about, here are 3 encodings that I just happen to know are ASCII compatible. They represent different types of characters, but for each of the ASCII characters, they have the same code point values, which you can see in that array. And then critically, it uses the same byte representation for each of those code points. So you can take an ASCII string and read it without any loss of data in any one of these ASCII compatible encodings. So about 90% of the encodings in Ruby are ASCII compatible. There's a really good chance what you're working with is ASCII compatible. The ones that you probably are more likely to run into that aren't ASCII compatible are UTF-16 and UTF-32. So again, this is kind of the distinction, because Unicode uses the same code point values for the ASCII code points. If you just look at the code points, you'll get the same arrays, but when you look at the byte representation, UTF-16 will use 2 bytes per ASCII character, and UTF-32 will use 4 bytes per. So since we have multiple encodings in the system, you might need to convert encodings from strings from one encoding to another, and that brings in this process called transcoding. And we've kind of looked at that throughout the talk. Every time we've called string encode, that's a transcoding process. Up until now, we've mostly looked at ASCII compatible encodings and ASCII strings, so there really is no conversion necessary. But here you can see the case where with UTF-16, if we call encode, it changes the byte representation to have 2 bytes per character. Critically, this transcoding process is error prone, or it can fail. And this might be the first type of exception you'll run into. So here, it's a bit of a contrived example, but I have a UTF-8 string with non-ASCII characters, and I'm converting it to ASCII. And then you get this undefined conversion error. And if you're not familiar with encodings, this can be really difficult to comprehend. The message has this kind of funny U plus with 4 hex digits rather, and then indicates the 2 encodings involved. Like, you just have to know that U plus means this is a Unicode code point value. And then you probably need to convert that from hexadecimal to decimal so you can look it up in the table. And if you're not familiar with that, you might just capture the exception and try to move on one way or the other. Another case you might run into is an invalid byte sequence. So this is a case where maybe you've read something from a network and you didn't get the full string. So you have like bytes at the end that don't really make sense for the target encoding you're trying to transcode to. And here you get a very similar type of message. Here, because we don't know that it's Unicode, the message now switches to a hexadecimal format. And again, if you're not familiar with this stuff, it can be really overwhelming. So Ruby gives us a few different ways to handle transcoding errors. On that string encode method, we can provide a couple keyword arguments that allow you to handle whether you encounter undefined characters or invalid byte sequences. If you're converting to an ASCII encoding and you want to replace either character, you'll get this question mark in the middle. So if you've ever seen a string that confusingly has a question mark in the middle, that's probably what happened. If you're dealing with non-ASCII data and it's Unicode, you'll get this one where it looks like a question mark and a diamond. And these are definitely ways of resolving the error, but you've lost data in the process. So you really need to be sure that's what you intended to do. Because if you put this into a database and it was a user's name or something, then the next time you read it back out, you're going to have these weird characters in there, and your customer might be curious why that is. Ruby also gives you the sledgehammer approach. So because a string is just an array of bytes with an associated encoding, you can just tell Ruby, hey, I know better, just change the encoding. And I've worked with teams that have done this, and it definitely gets rid of the error, but it is probably not what you wanted to do and will invariably lead to corrupted data. It exists for very narrow use cases, and it is important to have in Ruby, and a lot of it has to do with backwards compatibility. But if you see force encoding being used somewhere in your code base, it's worth taking another look at to see if that's really something you intended. Which brings us to the notion of broken strings. And this is another area where Ruby is a little bit different than its modern peers. Because Ruby, so first of all, strings in Ruby are mutable. You can just randomly change bytes in them, and you can override the encoding. It is possible to have a byte array for which the associated encoding is just utter nonsense. So here, I took that string tray and told Ruby, no, it's actually US ASCII, and it doesn't change any of the bytes, but now when you start performing string operations, you get kind of funny answers back. So you can check each string to see if it's broken, and there's this method calling it called valid encoding. You'd expect most strings you work with, this will return true. So you have this difference between valid and broken. I think you'll find if you look into it, a lot of people call them broken strings, but the API for it is valid string. Whether a string is broken or not is just a property of the string. Either it is broken or it is not. But Ruby allows broken strings to float through the system, which means you can make calls on broken strings, and the result you get actually depends on where the broken character appears in the string. This should be treated as an implementation detail and not something to rely upon. Please do not write specs or unit tests that check if the string's broken, that you get this answer back, because it really depends on the operation and where the broken character appears. But this brings us to binary strings. So a lot of this has to do with Ruby compatibility, but because, again, a Ruby string is just an array of bytes, and there really is no other mechanism for an array of bytes in Ruby historically, we came up with this idea of, well, we'll just have kind of a dummy encoding called ASCII 8-bit, and its aliased is binary, which I think is a more descriptive name. And this is an encoding that doesn't actually map to any characters. It just says this is binary data. And we use this when reading from network sockets or from files where we're just kind of reading arbitrary bytes and we don't know if we've read the entire thing and hit character boundaries and all that. Unfortunately, this encoding does report whether it's ASCII compatible, and this creates another kind of common situation where I see errors, where you can work with strings that are actually binary, but if they only consist of ASCII data, you can treat them like other strings and things basically work, and then the first time you get a multi-byte character, it stops working and no one knows why. Because this could be code that's existed for a long time, and now suddenly you have user-supplied input coming through a web form, or you're reading a file from someplace and you're seeing data you didn't previously expect. And all your tests might pass, the code might not have been touched for 6 months, but confusingly you have these errors now. Interestingly, binary strings by definition cannot be broken, so the valid encoding method will always return true in those cases. And yeah, they're really useful for I/O. So to give an example, we'll use string I/O so we don't actually have to hit a disk. And here we're going to wrap a multi-byte character string. And if we just read the entire string, we get back like a buffer, and its encoding is UTF-8. And that encoding is overridable, but that's the default internal encoding Ruby uses. If we rewind it so we can read from the beginning, but this time we give it a number of bytes, and here I'm just going to give it the total number of bytes of the string, now we get back a string that's ASCII 8-bit. And that's a bit contrived, but it gives you an idea of how making a call a certain way, you can get back data you didn't quite expect. The real case you might use this is if you're trying to read data in chunks from either a file or network. Often you don't want the whole thing in memory, so you read in these fixed number of byte chunks, and then if you pass it on to another part of the system, that system needs to realize that it's not really working with string data, it's working with binary data. In this case, I structured it such that each of the chunks will get one of the 2 bytes for that C with the CDL character on it. So both of the chunks will actually be broken. And this is also why Ruby does allow broken strings to exist, because if you concatenate them back together, then you have the full byte sequence and it's valid UTF-8 data. All right, so with all that, we'll build up to a fun little trick you can show your friends when you go home. We'll start by taking 2 strings. We'll just create one as a string literal and one by calling string new, just 2 different ways of creating strings. We can check if they're true. We get back what we expected, I hope. And now we're going to use that fun little C++ operator to shovel bytes into the end of it. This will grow the string if needed, and this is typically how you'll see binary data added to a string. Now we'll check if they're equal, and suddenly they're not. So what gives? Take a look at the byte data. Now one of them has 2 bytes, and one of them only has 1 byte. Well, what gives? The problem is that an empty string literal and string.new are not actually equivalent. One will create a UTF-8 string, and one will create a binary string. And this is another way I've seen people really get themselves into confusing errors, because they'll want to do something like reading bytes in chunks, and they'll allocate a buffer, and they're just so used to allocating as an empty string that they don't really think much about the encoding. And that shovel operator, what it actually takes is not byte values, but code point values. And that 0x80 hex character takes up 2 bytes in UTF-8. So that brings us to the next kind of, I guess, semi-novel feature about Ruby, is because we have different encodings floating through the system, with different strings with different encodings, we need them to interact with each other. Ruby really puts an emphasis on the developer experience, as I'm sure you're aware. So Ruby does not want to force you to transcode everything to the same encoding. Because if everything's the same encoding, then these operations are pretty trivial. But again, 90% of the encodings are ASCII compatible. A lot of the time you'll be working with some form of ASCII data. So in those situations, we can concatenate 2 strings that are ASCII only trivially, regardless of what the encoding is. So we can check this compatibility ourselves. Going back to the encoding class, there's this compatible question method on it, and you can give it 2 objects. What the behavior of that method is changes depending on the type of objects. If you give it 2 encodings, it tries to give you the one that has the superset of all of the available code points. So if we check if US ASCII and UTF-8 are compatible, we get back an answer of UTF-8. And this is the first thing that kind of throws people off. Even though it ends in a question mark, it doesn't return a Boolean value. It returns an encoding, or it returns nil. And here, if we flip the arguments, it doesn't matter. In the argument order, we get back UTF-8. And then if we have 2 encodings that aren't compatible, you just get back nil. So this is something you could check if you wanted to be a bit more defensive. Confusingly, things change when you give it 2 string arguments. The documentation says the rules for strings depend on whether the strings are concatenatable, and that involves a kind of confusing set of rules. The best I can put it is Ruby really tries to make sure the operation succeeds. So it looks at the contents of the strings in addition to the encoding to see if the operation can proceed. But here you can see that argument order now matters. Whether you do A plus B or B plus A, you get a different encoding. Even more confusingly, if you have 2 encodings that say they're not compatible, strings in those encodings might be compatible. So if you're trying to, again, be a bit defensive, you really need to make sure you're passing in the right type of object, because just giving it an encoding will give you an incorrect perception of how the string operation will proceed. But if the strings truly aren't compatible, then you will get back nil. But there are also exceptions carved out for empty strings. So again, Ruby checks the contents of the strings. If US ASCII and UTF-16, generally you can't concatenate them, but if one of the two of them is empty, then suddenly the operation proceeds. So your notion of whether two encodings are compatible really depends on the code points available in both encodings, whether they use the same byte representation. Then when you get into the string operation level, it even depends on the contents of those strings. So far we've kind of looked at just encodings for strings, but there are encodings for other objects. The ones you're more likely to run into are symbols and regular expressions, and then I/O has an associated encoding like we looked at. And these pop up inside the standard library in various places. I don't have time to get really into it, but there's different ways to override what the default encoding is when you're reading from files or when you're creating strings. Ruby will default to UTF-8 for internally created strings and ASCII 8-bit, or that binary encoding, for external data. But we can take a string and we can convert it to a symbol. So we got a string, it's UTF-8, convert it to a symbol. We can check that symbol's encoding. It's also UTF-8. And if we just want to round trip it and convert that symbol back to a string, we get back UTF-8. Great, that's what I hope everyone expected. However, if the string consists of only ASCII data, Ruby has an exception where it will change the encoding on the symbol to US ASCII, and then that kind of sticks with the symbol. So if you convert the symbol back to a string, that string will now have the US ASCII encoding. And most of the time this doesn't matter. US ASCII and UTF-8 are ASCII compatible. It gets a little trickier if you have changed the default encoding. But the point is you could be working with strings in different encodings and not even really realize it. This comes up in numerics as well. So all of the digits are representable in ASCII. So if you convert integer or a floating point value to a string, that will have the US ASCII encoding as well. So which brings us back to kind of the title of the talk. How many encodings do you think your application uses? I posit you probably have 3, even if you don't realize it. So a lot of people think everything is just UTF-8, because that's what Ruby defaults to. But that's only true for string literals and then particular operations. If you're converting symbols or numbers to strings, they're going to come in US ASCII. And if you're dealing with I/O at any level, which most applications that need to interface with the outside world do, then you could have binary data as well. So why does this matter? Well, if we get back to that encoding negotiation process, if the operation is on strings with the same encoding, then the derived encoding is trivially the encoding in use. And that's a very quick operation. But if they're not the same encoding, then we got to run through that kind of long set of rules that checks if these two strings are compatible. And that rule involves looking at every character in the string. So you can have a linear scan of the string that you don't really expect just because you're using 2 different encodings. Ruby tries to hide some of this from you. So Ruby, again, supports 100 some odd encodings out of the box, but it tries to be pretty equitable. So rather than optimize for particular encodings, it optimizes for properties of those encodings. So US ASCII, every code point can be represented in a byte, so it's a fixed width encoding. Every character has the same width. Just like UTF-32, every character is 4 bytes. So if you're using the index operator on a string, you can really trivially figure out where to jump to because you just have an array of bytes and you can work out the index. But with UTF-8, if you have multi-byte character data, you have to figure out the character boundaries for every single character. There are various ways to shortcut, but if you're trying to get the last character, you basically have to walk the whole string. Additionally, because Ruby allows broken strings, you can't even use particular tricks in UTF-8 to hop through. When you look at the encoding for UTF-8, the first byte in any character tells you how many bytes that will take up, but that doesn't work when you allow broken strings to float through the system. Yeah, I went too far. Ruby has this cached metadata associated with strings, something called a code range. And as long as the string doesn't change, the code range will stay the same. And this basically just tells you, is the string consisting only of ASCII data, and is the string valid? And if those properties hold, then Ruby is able to optimize operations on those strings just like as if it were a fixed width encoding. So this is one of the things that again, could take an operation like string concatenation and change it from basically constant time minus having a copy memory to a linear time operation because you got to scan the whole string. From a behavioral impact, when you're dealing with encodings, you need to be in agreement with encoding all the way through the system. So it doesn't help if you're working with UTF-8 data, but your database isn't, because you're going to start stuffing strings in there, and they're going to get corrupted along the way. And likewise, if you're reading stuff from files, or if you have user forms being submitted, you need to check the encoding. Like for a long time, ISO 8859.1 was a really popular web encoding, so this might be a weird one that you run into. In addition to a database encoding, databases also have this notion of collation that impacts operations like how things sort. Unfortunately, even systems that implement the same encoding can disagree on this. So for instance, if you're using Postgres, it will actually sort UTF-8 strings differently than Ruby will. They disagree on the relative precedence of operators. So that can be another really confusing error to run into, something to watch out for. And again, like the way a lot of this stuff breaks is, particularly if you're an American company, you're primed to think of just strings and ASCII data, but you're serving an international audience, and now suddenly you have someone submitting strings in an encoding you weren't expecting. And your seed data might just use all ASCII data, maybe using Faker or something, and you're not forcing it to give you multi-byte characters. So this is one of the reasons I think you really should try to be aware of encodings. I hope that you'll be better equipped to solve some errors. So tying this all together, I'm happy to say that in Ruby 3.2 there have been changes to try to speed some of this up. A lot of this was spearheaded by a colleague of mine named Jean Boussier. He goes by Beirut if you look at the Ruby commit list. So one of the ways we're speeding things up is we're just invalidating the code range value less frequently. So if we can trivially derive what it should be, then we can avoid this expensive scan through the string. This also has benefits for copy on write because the code range value is lazily computed, and a lot of operations will actually populate it. So if you fork and then you have to scan that string, you'll basically trigger a metadata write and have to have a fault. And then string concatenation is now faster. This is one area that John's been looking at quite a bit. Here we're modernizing Ruby a little bit to really actually optimize for the three most common encodings, the ones that Ruby defaults to, and they all happen to be ASCII compatible. So in those situations, we can more trivially figure out if the encodings are compatible, and that helps the concatenation operation. There's more room for optimization here, so I'm really excited that there'll be more string performance coming in future Ruby releases, but if you're looking at the Ruby release notes, now you have a better idea of what that work's all about. And yeah, that's about it. So we've looked at encodings, just the general concept, how they apply to Ruby, Ruby's different mechanisms for transcoding and changing the encoding on strings. There's some history here, both in Ruby and just in computing in general, for why the encoding system is kind of messy, and we have hopefully a richer appreciation for how this can impact performance and the behavior. I've got a slide here for some resources. I'll just publish the slides, but these were links I thought might be helpful. I wrote a blog post on code ranges that gets into the details of how those work, and I've linked to some of the PRs from Ruby 3.2 so you can see how some of the changes were made. And that is it. Thank you for your time.